In this segment, we'll do a bit of assembly debugging, and we'll demonstrate a debugger. You should follow along with a Pi of your own using the example prg2bug.s code, which is shown up here on the diagram as well. This is also a chance to learn or reinforce your Unix and VI skills. All the work we'll do on the Pi will use the command line Unix and VI editing interface. They're pretty old technology, 1970s, 1980s, but still widely used professionally, so it's worth your investment to learn them. So I'm going to bring up my Pi here, and as I said, please do the same for yours. I'm going to start with an ls command, which will demonstrate that I have in my directory a prg2bug.s file ready to use. You should do the same, probably by copying the file from the website onto another machine and then uploading it from that machine to your Pi. Accessing the web directly from the Pi may be another option depending on how your Pi is configured. One way or another, get that .s file available to use. Now, let's start by looking at a few assembler errors. If the assembly code doesn't obey syntax and punctuation rules, the assembler reports errors, just as a compiler would for high-level languages. So, please now try assembling prg2bug.s. And you may have paused to do that. I'm hoping people remember that the way to do that is to do as prg2bug.s and then give it a suitable .o file name. And what we wind up with is a couple of assembler errors. Now, those are being reported on line 7, as you can see, and on line 18. The assembler reports errors just like compilers do, but often, like compilers, they don't give very clear error messages, especially the one for line 7, bad instruction loop top. Let me pull this aside and we can look at the code we have in the diagram. Loop top isn't an instruction, bad or otherwise. It's a label, right? But see if you can see what's wrong here. And if you weren't able to see, the problem is that loop top needs a colon after it to be marked as a label. So that's one error. The absence of the colon makes the assembler think it's the start of an assembly instruction. Now the line on, or the bug error on line 18 is perhaps a little clearer. Immediate expression requires a pound prefix, although immediate expression is somewhat unfamiliar jargon. Immediate is assembler ease for constant. So clearly we missed the pound before the 1. Now, I just fixed those in the diagram, but we will need to fix them on the Pi as well. So let's use a VI session on the Pi and try again. Now, this requires the steps below, with hints provided in some cases. Use a VI help sheet if you don't already know the editor. What you're going to need to do is open VI on the file, navigate to the text to change, and there you may find arrows, HJKL keys, or a slash key to search for patterns, useful. Edit the text, and there X, CW, I are potentially useful commands. Save the changes, ZZ or :WQ, and importantly, not Control-Z. That's a bit of a trap on Unix systems. Control-Z is often used to undo in modern UI, but not on Unix. It means pause the program without saving anything and leave it in the background, which usually results in all sorts of a mess. So no Control-Zs. Now, please proceed to modify your prog2bug.s file so you know you can do that, and then I will show how to do it myself once you're done. Again, coming back from what might have been a bit of a pause there, I'm going to do vi prog2bug.s to bring up the file. I'm using, because I'm a little old school, J to go down, though arrow keys would have done the same. I'm going to use arrow keys to go over, and then I'm going to use actually one I should have mentioned, an A command, which will add after the current letter. I'm now in insert mode, which is something you should be familiar with from your VI help sheet, and I'm inserting a colon and then escape to stop the insert mode and go back to normal editing mode. Now I'll go down now, or if I want, I can simply search for a R7 with a slash R7 and go down to where R7 is, and then I'm going to use the I key to insert a pound here and escape again to get out of insert mode, and then finally ZZ to save it. You don't have to be a VI expert, but you do have to know the basics to work with this code we'll be doing on the Pi. Now, with those two files, you should be able to successfully assemble the program, as I just did. But then, what happens when we link the result? LD we get a linker error. Now, such errors generally have to do with misnamed or undefined labels. So to be clear, you can get errors both from the assembler for basic syntax problems and from the linker for deeper things involving labels. The linker's job is to link together different pieces of code, like your program and the libraries it uses, and labels have a lot to do with that. In this case, see if you can see the problem. If you think about it, we mislabeled start. It should have been underscore start. So we'll fix that. And you should fix it as well, of course, using a VI session. Doing an I there with an underscore and fixing it in the global line as well. A dot, by the way, repeats commands, which I found convenient there. We're going to have to reassemble, right, to get the new label assembled, and then do a load, and we should now be able to run the program. But what happens when we run the program? Looks like an endless loop. Now, if this were a C program, you might insert a printf. But the best we can do in the way of output so far is an exit code, and that's not going to help find out why the program is looping. Instead, we'll use a debugger. Start by Control-C'ing this to stop it, and do the same, of course. The GDB debugger helps you debug assembly programs. You run the program under the debugger's control. Debugger commands let you stop the program, inspect the contents of registers, advance the program instruction by instruction, and so forth. To use GDB, you first assemble your program with a debugging flag. So we're going to add after the AS, and you should do the same, a -G. The -G flag tells AS to include the assembly code and its labels as additional information in the .o file, along with the machine language translation. The LD command copies this information into the final executable, and that allows GDB to read it from the executable when running your program, in order to give you an assembly language listing of the code as part of the GDB session. Now, run GDB with the debug assembled program as an argument. Thus, you'll get a block of initial output, which you can usually just ignore. At the GDB prompt, parenthesis GDB down there, type list. This gives you a partial list of the assembly, 10 lines or so, using the information that was inserted by -G. If you want more lines, give the start and ending lines as list arguments, so list 1, 15, for instance. As we'll see, you can pause the program at any point during its execution, and you can list the assembly code anytime the program is paused. The list command will show about 10 lines surrounding the instruction you're paused at. Now, the command run actually runs the program under GDB control. The program will behave exactly as if you'd run it normally, but if you stop it via Control-C, as I'm about to do here, GDB resumes control and shows you what line was executing at that point. Trying that for our program, we find it was executing a line within the loop, the add R0, R0, R1 in this case. A list command will show the surrounding lines if you would like a reminder. Let's see what's in the registers. Run info R. This displays all the register content, as you can see. Note that R13 to R15, by the way, down at the bottom, do have special names, SP, LR, PC. We already know that R15 is the PC, so that name is no surprise. We'll see why R13 and R14 are called SP and LR in a later segment. And there's a 17th register, CPSR. That's the PSR register we briefly discussed earlier. More on that later too, of course. Each register's value is given both as a decimal value to the right and a hexadecimal value in the middle column. You read the decimal column if you care about the register's numerical value, and you read the hex column if you care about the particular pattern of bits in the register. Just two different ways of looking at the same content. Now, the registers we're most interested in are R0 and R1. And here something strange is happening. R0 has a huge value in it, and R1 is still at 1. It hasn't increased at all. At this point, you might have noticed that line 13 is the problem. It adds a 0 to R1, so the loop goes forever and R0 gets increased by a lot. But if we were still baffled, we could examine the program's behavior more carefully. Let's insert a breakpoint. A breakpoint is a marked instruction at which you want GDB to automatically stop the program so you can see what's going on. Maybe we'd like to stop at line 11, the top of the loop body. We do this with the B command, followed by the line number. And we can see that we have a breakpoint now at line 11. Then restart the program via a run command. You'll be asked if you want to start from scratch. You can if you like, or you can continue from the point you were at. Let's start from scratch. Find the program stops automatically at line 11, our breakpoint. And info R command will show the register content. R0 and R1 are 0 and 1 at this point, as expected. And we can resume execution via cont for continue. And again, we'll stop at line 11 on the second loop iteration. Now, both R0 and R1 are 1. Let's try advancing the program one instruction at a time via step. That gets us to line 13, for instance. Each step command moves the program forward one instruction, and you can inspect register content after each instruction. I think by now we'd surely notice that R1 is not changing. Assuming we're done and know the bug, we can exit GDB via quit. It'll complain that you have a currently running program. It's safe to quit anyway. Now, there are many more GDB commands, and GDB's help command offers documentation on them. So, an in-lecture question. Use GDB help to find out what command will list all the current breakpoints. Coming back from a pause there. Info breakpoints would do this, per the help status command. There's help. And I looked at help status since that was an option. Status inquiries seemed appropriate. And right down there near the bottom is info breakpoints. So here's a quick GDB summary. You assemble with the -G flag. You run via GDB and your program executable. You use GDB commands, list, run, cont, b, info r, and step to figure out what's happening, and you end the GDB session with quit.